and that's going to be multiplied with the Jacobian matrix of G. G maps two variables to two variables, so its derivative is going to be a matrix of two rows and two columns. So we're going to have Jacobian of G at S and T. Now these are linear functions, so partial derivatives are just a constant matrix, so we'll have dx ds, dy ds, dx dt, dy dt. Columns correspond to variables differentiated with respect to. Rows correspond to opponent functions. So when we compute these partial derivatives, because these are linear functions, we just get constants. 2, 1, 1, minus 2. So now, when I apply the chain rule, alright, I'm going to write it out twice. First way is in terms of the derivatives, so I'll be writing df dx or dx ds, so you can see what the process is. And then the second way with the actual functions involved. So what we have here is a scalar valued function of two variables. So the gradient of f composed with g evaluated at s and t is going to be the dot product of the gradient of f evaluated at g times the Jacobian of g evaluated at s and t. So that would mean df dx, df dy, dx ds, dy ds, dx dt, dy dt. So we multiply this out, we're going to take the dot product of this row with this column. So we'll have df dx, dx ds, plus df dy, dy ds. So this is partial of f composed with g with respect to s. So s is covered by this first component. The other component, we take the dot product of this row with this column. So we have df dx, dx dt, plus df dy, dy dt. So this is a partial of the composition with respect to t. So if you're given any function like this, where you're composing a scalar valued function of two variables with a vector valued function of two variables, this is the formula that you can use. This is what the chain rule looks like in partial derivative form, what you see from a single variable chain rule. And you can see this cancellation here. If you don't see something like this, you mess something up. So now we can apply this to the actual functions involved. So we're going to get 2, and so for x, I'm going to fill in 2s plus t. For y, I'm going to fill in s minus 2t. 2xy plus y squared, and then we have x squared, 2s plus t squared, plus 2xy, plus 2s plus t, s minus 2t, running out of room, and that is multiplied by this matrix, 2, 1, 1, minus 2. So now we take the dot product of this vector with this column for first component, and then we take the dot product of this row with this column. So we're going to get 2 times plus 1, 2s plus t, s minus 2t. So all of this, that's a derivative of the composition with respect to s. And then the other component is the dot product of this entire row with this column. So we'll have 1 times 2s plus t, s minus 2t, plus s minus 2t squared, plus minus 2 times 2s plus t squared, plus 2s plus t, s minus 2t. So this is a process, multiplying the gradient of a Jacobian. This is how we handle the case of composing where the inner function is a function of several variables. Like in this case, we're going to get a matrix here that we multiply this gradient with. So if f had been a vector valued function of two variables, we would have had two Jacobian matrices, and those are what would have to be multiplied, and that would be even nastier. This is the vector valued function that takes in two variables, outputs two variables. G is also a vector valued function. It only takes one variable in, two variables out. So f, xy is a vector, x squared y, xy squared. G, function of single variable t, is components cosine t and sine t. The composition is a vector valued function of one variable, so it's going to be cosine squared t sine t for first component, and then cosine t sine squared t for the second component. So to compute the derivatives of this function, which is just going to be ordinary derivatives with respect to t, the final result is a function of one variable, but it's vector valued. So the derivative of a composition with respect to t is going to be the Jacobian matrix of f evaluated at g of t times g prime of t. So we have a matrix being multiplied by a column vector. Now, the Jacobian evaluated xy is going to be, so I'll write this as f1 of xy, f2 of xy. So we have f1 with respect to x, f1 with respect to y, f2 with respect to x, f2 with respect to y. So now we can differentiate these functions with respect to x and y. So we'll get something nice and short for a change. 2xy, x squared, 2xy. And then, of course, the derivative of g It's a single variable function, no problem to compute that. d prime of t is just going to be minus sine t cosine t. So then when we apply the chain rule, so the derivative of this now single variable function with respect to t, it's going to be this matrix f2x, f1y, f2y times dx dt, dy dt. So when we carry out the multiplication, we're going to get a vector, two elements. So we'll have the f1 dx, dx dt plus f1 dy, dy dt. So that's the derivative of the first component function with respect to t. So this one. Down below we'll have the f2 dx, dx dt plus df2 dy, dy dt. So now we can go ahead and compute that with these partial derivatives, because what we have here is 2xy, x squared, y squared 2xy, but they're evaluated at, actually let me fill in that this is a function of t, 2x of t, y of t, x of t squared, y of t squared, 2x of t, y of t, times derivative of g minus sine cosine. So now we can carry out this multiplication. We have this row dot product with this one and only column. So we'll have 2 cosine t sine t times minus sine t plus cosine squared t. So that's the first component. The other component, we take this row dot product with this column. So we have sine squared t minus sine t plus 2 cosine t sine t times cosine t.